Assalamu alaikum. I'm Janatul Firdaus. This is my second round submission for the ML intern position of DataSynthis, and I was given set A. So for the first question, I actually used a recursive algorithm that efficiently returns the sum of all the values within a given range here. And the key idea is that since ABL trees are balanced binary search trees, we can actually skip the unnecessary subtrees that are not given in our range. So first, the general intuition is that if no root is provided, we will directly return 0. If the current node's value is smaller than L, which is lower than the value of the range, we skip our entire left subtree. And if the value is larger than R, we skip the right subtree. Otherwise, we will keep adding the value of the current node and keep it recursing on the both sides. Let's say, for example, we have this tree right here, and we want the sum from range 7 to 15. So we will start from the root here. We will first check if the value is within our range, and it is indeed in our range. So we will first go to the left, and we have this value right here, 10. This is also in our range, but these two values aren't in our range, and this will be skipped according to our algorithm here. And similarly, we won't consider these two nodes in our summation as they are outside our range. So we don't even need to calculate any of this, and we can just use this value according to our algorithm. This method is actually efficient as it does not require us to visit all the nodes in the entire tree, as the tree might actually contain millions of nodes, and this will save us time for balanced trees. For the follow-up question in our ML part, let's say we added another node into our existing subtree. But if we recalculate the entire sum once again for a different range, it will be very redundant because we need to visit all the nodes once again. So currently we have the nodes value in each node, but we can also store a sum of the value and its descendants in each node. So when another node is added, we will only be recalculating the sum along that path, which is here. And that will save us a lot of computational time for ML models that may actually depend on this feature. Let us move on to the next question now. When ML models are deployed, their parameters such as the weight files can be huge, sometimes gigabytes in size. We cannot actually scan the entire database every time we need to update or load parts of those weights, as this will be very time consuming and inefficient. Hence, we use tree-based indexes like B trees to store and find data efficiently. Let us look at this example here. A B tree keeps the data sorted and balanced. Each node can store multiple keys, such as here, and every key represents a range of values in its child node. For example, this is our node here, and this is the child node. When we search for a key, we compare it against the key in a node and follow the correct branch, so it takes us only few comparisons per level. Let's say we want to find a weight 22. We start at the first level and find 9. 22 is greater than 9, so we go to the right and we find 30. 22 is less than 30, so we go to the middle and find the child. And similarly, we compare it and find that 22 might be in between 19 and 26, so we go down another level again. And in the same way, we find 22. So this is just 3 steps, even if the database has a lot of entries, as you can see here. Imagine if the numbers were set as a list, but not as a B tree. Then, for example, we had to search the number 41. So what would happen here? We would actually have to search the entire list, which would give us a time complexity of big of n. And but if we use this B tree right here, it would similarly take us only 3 searches. And I mean, it would only take us 3 steps to find the number 41. Even during insertion, the new weights are added in a sorted order. Let's say the last node had an overflow here if we wanted to add something here. So in B trees, the node would actually split in half and one key would be passed up to the parent, and this would still keep the entire B tree balanced, guaranteeing the same insert time even in very large datasets. Now for the follow-up question, in recommender systems, embeddings for users and items are actually sorted by IDs. So during interface, we might need to quickly retrieve those embeddings. A B tree would index would let us locate them efficiently without scanning everything. Since these trees are balanced, if we add new users or items, the lookups won't slow down, keeping the real-time recommendations fast and stable. We could think of the B tree like a phone book organized by the first letter of a name. So instead of flipping all the pages, we just jump straight to the right section and keep narrowing further down, just like a dictionary. And that's how the database finds our model weight or the embeddings quickly. For the next question, my approach here for designing the algorithm uses a communication-based algorithm which is similar to a distributed prims algorithm. Let's say we have four different nodes A, B, and C, each stored on different machine in a distributed system, and each edge represents a connection with the communication cost, and our goal is to form a minimum spanning tree, meaning that we connect all the nodes with the lowest total cost without creating any sort of loops. Let's say we choose node B as the starting vertex. So we set the key of B as 0 while the other nodes are set to infinity. So our MST will now contain only node B at the very beginning. All right. So after communication, the nodes will find out that the lowest weight is 1 between B and C. So we will now add C to our MST. Then the next smallest connecting edge from A to B with 2 right here. And we continue doing this until all the nodes are present in the MST. And here is the algorithm that I had designed. First, there is initialization where we choose one node and start with cost 0 and the rest is set to infinity. Then the nodes exchange messages to learn about the weights, just like how we found out that B has these connecting edges. Then each unvisited node keeps track of the smallest edge, connecting it to the MST. So every node connecting with each other now knows which uh, no edges are connected to which ones. Then the node with the smallest connecting edge now joins the MST, which we did here, like adding the C because this was the smallest weight connecting with B. And this will keep, this both step will now keep repeating until an entire MST is formed. This approach is efficient in distributed system as each node only talks to its direct neighbors, like here, and instead of a central controller, for example, reducing the communication overhead and keeping the process scalable. And in machine learning, MSTs are useful for sensor network optimization, for instance, when collecting EEG brain data, as I did for my thesis as well. Each electrode is a sensor node, and since many electrodes record redundant signals or signals that we might not need, we can use MST to keep only the most representative connections, the ones with the strongest correlation but lowest redundancy. So the ML model will work faster with fewer but more informative features. Now for the final question. In slab allocation, memory is actually pre-divided into fixed size chunks like this, for example. So when we need to store any type of object, we just drop it in one of those empty slots. So there is instant allocation and we can delete those instantly as well. But if an object is too big, we might need multiple slots, and that would actually leave small wasted space. For example, if an object takes this entire chunk, but half of these or less than half, this space will totally be wasted because no other objects can be allocated here. We need to move on to any of the next chunks. But on the other hand, garbage collection does not have this issue as they dynamically allocates the memory and any object can actually go anywhere. But the problem is that once in a while, the system pauses everything to clean up the unused memory. That pause can actually delay the real-time systems, which in case of online ML serving like real-time recommendation, thousands of requests per second are processed. And the key metrics of those type of cases are latency. And the users will actually expect fast responses. So the occasional pauses like few milliseconds or few seconds can actually degrade the user experience. And as slab collection provides the deterministic and constant time memory operation, like we actually can put objects in any of the free chunks. So it is actually better suited for this latency critical system and garbage, even though the garbage collection runtimes do offer convenience, like we can actually allocate the memories dynamically, but the unpredictable pauses every now and then can actually hurt the responsiveness. This concludes my explanation for all the four questions. Thank you for the opportunity to participate in the second round.